AIMCOM workshop session B. In this session, we have three invited talks. The first talk is from Qingqing Wu from the University of Macau. His title is Toward Smart and Reconfigurable Environment, Intelligent Reflecting Service Enabled 6G Value Networks. Beforehand, I'd like to briefly introduce Qingqing Wu. Professor Wu is currently an assistant professor in the Department of Electrical and Computer Engineering at the University of Macau, China. He was a research fellow in the Department of Electrical and Computer Engineering at the National University of Singapore. His current research interests includes intelligent reflecting service, unmanned UAV communications, and memo transceiver design. He has published over 70 IEEE journal and conference papers. Professor Wu was the recipient of many awards like IEEE WCSP Best Paper Award, the Outstanding PhD Sensors Funding in Shanghai Jiao Tong University in 2016. He is the lead guest editor for the IEEE journal on select area in communication, or GSEC, on UAV communications in 5G and beyond networks, and the guest editor for IEEE Open Journal of Vehicular Technology on 6G Intelligent Communications, and IEEE Open Journal of Communication Society on Reconfigurable Intelligent Service-Based Communications for 6G Value Networks. So let's welcome the talk from Professor Qingqing Wu. Thank you. I will quit the sharing. Thank you.
Okay, can you hear me?
Yeah.
Okay, let me share my screen. I think. Okay. Okay. Hi, Rongpeng, can you see my screen?
Yeah, that looks great. Yeah.
Okay. Let's get started. Okay. Thanks for the introduction and also the invitation from the Professor Li. And also, hello everyone. Welcome to my talk. This is Qingqing Wu from the University of Macau. And I'm also affiliated with the State Key Lab of Internet of Things for Smart City, which is a newly established lab. I changed a little bit on the title of this talk, but it's essentially the same. So the title of this talk is Faster, Smarter, and Greener, Intelligent Reflecting Surface for 6G Communications. So basically today I will talk about a new technology we proposed for the first time, that is intelligent reflecting surface. And it has been recently considered as one of the most promising technologies for 6G. Here, the faster, smarter, and greener means that it helps achieve a higher data rate and in terms of the system design and optimization. And it is also smart. And also in practice, it is of low cost, low complexity, as well as low energy consumption. So this is our objectives towards this technology. This is the outline of this talk. In the first part, I will briefly talk about some basic background and applications of the IOS. In the second part, I will talk about some three major challenges of the IOS from the communication and signal processing perspective. And last, I will conclude this talk and also point out some future directions. Okay, let's start from the first part. So this is a wireless network evolution, right? As we can see that almost every 10 years, our telecom industry develops a new generation wireless system to change the way we communicate, and also other industries. Right now, 5G has been deployed in some countries, and we are at the very beginning of the next 10 years, right? So several countries and leading IT companies, they have announced their initiatives towards 6G. So definitely the main driver to support new applications like the augmented aerial vehicle communications and virtual reality and industry automation and autonomous driving, right? As we can see here. So, but when we look at the communication requirements of these applications, as we can see in the below, they have spanned a huge plane in terms of the system throughput, latency, and reliability. So where the current 5G technologies may not satisfy all of them, right? For example, the current 5G technologies only support 1 to 10 gigabits per second, and this is still far less than that required for the virtual reality, that is terabits per second. So this means, and also on the other hand, in practice systems, the 5G technologies also have a lot of implementation issues, as we got some feedbacks from the operators. Like they have a high cost and energy consumption is also very high. Also, the implementation complexity is also very high. So this suggests that we do have the need to develop a new technologies, probably for 6G. So this also motivates us to look back on the fundamental capacity formula established by Shannon, right? So in the last 70 years, our maximum communication data rate has been governed by this equation, right? And even in the 5G system, the underlying assumption is that the wireless channel between the base station and the users are random, which means that we just optimize the transmission and reception. We didn't make any effort to control the wireless channel between the base station and the users. So in this case, we propose a new paradigm shift that is for 6G, that is called a smart and a reconfigurable wireless environment. So this is a brand new and completely different idea as compared to 5G. Because we are going to control the wireless channels instead of optimizing the transmission and reception. So the key enabling technology proposed for it is intelligent reflecting surface, or simply IS. And by using the IS to control the wireless propagation channel and to control the radio environment between the transmitter and receivers, we have a higher flexibility and we have a higher degrees of freedom. Improve our system performance with even with much lower cost and complexity. So what is IS, right? And this is one very simple architecture. As basically the IS is to modify the signal propagation, as we can see here, and by highly controllable reflection. So the keyword here is highly controllable. And this is very different from our current walls, windows, or ceilings that just reflect the signals randomly, right, in different directions, and also lead to substantial power loss. So more specifically, as we can see here, the IS is composed of a massive number of reflecting elements, and each of them is able to reflect the signal with a controllable reflection amplitude and a phase shift. So by coordinating the reflection of all the elements, we can achieve the, for example, as we can see here, three-dimensional beamforming towards many different users to improve the user receive power. So, and also, even when the user moves, right, as we can see here, the IS can still track the users, right? Even the incident signal direction do not change, but the reflection beamforming can still track the users. So this is actually achieved by using a smart controller, which is AI empowered and in charge of the signal processing and mode switching tasks of the IS. So here I briefly explain why do we call it IS, right? So surface, the first word is the surface, right? Because it composed of massive number of reflecting elements, and considering its sub-wavelengths, and from a certain extent, we can call it a surface. And the next word is the reflecting, because this is actually the fundamental difference between the IS as well as the traditional wireless technologies. For example, the massive MIMO or relay, they are both based on the wireless transmission and reception. It's not the reflection here. So this is one fundamental difference. And the last word is the intelligent, which means that it is intelligent hardware, which means that for each of the elements, we can control its reflection amplitude and phase shift. And also in terms of the communication protocol and signal processing, I mean, from the software perspective, it is also intelligent. So it's intelligent in both hardware and software. And also in future, we may integrate some, because we need to tune the amplitude and phase shift, so we have some power consumption, but this is far below than the data consumed by the massive MIMO relay. So, and in the future, we may integrate some energy harvesting or wireless power transfer techniques to achieve the fully passive concept for the IaaS. So here is the reflection model. As I mentioned, this is element is going to reflect the signal, right? With the reflection amplitude and the phase shift. The reflection amplitude is beta and the reflection phase shift is theta. And theoretically, we do want that the reflection amplitude and the phase shift can be continuously tuned. For example, between the values of 0 and 1, right? Phase shift can be tuned between the values of the 0 and 2 pi, right? But in practice, due to some considerations about the cost, complexity, as well as the hardware imperfections, so we usually have other types of reflection amplitude and phase shift. That, for example, the discrete, like a low resolution reflection amplitude and phase shift, all coupled, because the reflection amplitude and phase shift probably they may be coupled together. So, and also there are two other special cases. For example, when beta n equals to 0, which means that the reflection amplitude is 0. It means that this element is in the absorption case, which means that no signal will be reflected back. And in the other extreme case, when beta n equals to 1, it means that this element is in the full reflection case. So all the incident signals will be reflected back, but can deal with different phase shift. So in practice, because the IaaS is passive, we have to use a large number of reflecting elements and put it in a vector form. This is to use the diagonal matrix to multiply incident signal vector X. So here, I briefly explain why this is a diagonal matrix. Because for each of the element here, because it only reflects the signal received by this element, not by any other elements. So it's kind of a one-to-one mapping. So this is why this is a diagonal matrix. There is no joint inter-element signal processing. So this is a practical model for the reflection amplitude and phase shift. We call it a discrete amplitude and phase shift. Like here, they only, for each of the reflection amplitude and phase shift, they only have very limited discrete values. And this is one uniform quantization. They're uniform quantized between 1 and 0 and 2 pi. But in practice, this may not be the optimal scheme. I mean, the uniform quantization, right? Because, for example, give you 1 bit to control the reflection amplitude, you can either choose 1 and 0 or 1 and 0.5, right? And so in practice, the performance may depend on the statistical, a lot of factors. So for example, the statistics of the channel state information or any other channel state information. And we also have two special cases. One is the phase shift control IaaS, which means that the reflection amplitude is fixed as a given value, and we can tune the phase shift. And correspondingly, the other case is that we fix the phase shift, but we can only tune the amplitudes, reflection amplitudes of each of the elements. So there are two. This is the two practical types of the IaaS. And this is a very simple point-to-point baseband signal model. As we can see here, the incident signal, the signal transmitted from the transmitter X will go through 3 processes. The first one is from the transmitter to this element that is given by the HN. And the last one is given by the GN, that is from this element, reflecting element, to the receiver. And in the middle point, that is a reflection process. That is just I mentioned the reflection amplitude and phase shift achieved by this element. So according to this baseband model, we can derive its path loss model from the transmitter to the receiver. So for each of the link, it follows from the typical path loss model, which is composed of reference distance path loss, and also path loss data scales with the distance of the transmitter and receivers. So the total path loss from the transmitter and receiver is given by this one, and that we call it product distance path loss, which means that the total path loss from the transmitter to the receiver is given by the product of these two path loss. And at the very beginning of in this research area, there has been another path loss model that is called a sum distance path loss model. They consider the signal propagation from the X to Y by adding the distance of these two links together. But this is a very nice result, but it is later proven to be wrong, to be incorrect. This is mainly because it has some assumptions. The first one is that it requires the surface to be infinitely large. And the second way is that it is only applicable to the free space propagation. It is not applicable to other propagation like their scattering or other cases. So because for each of the reflecting element here, it is very small. It is in the order of sub-wavelengths, so we cannot apply the sum distance path loss model. We should apply the product distance path loss. And here are some applications of the IRs for wireless networks. As we can see, the first one is for Zoom user, right? We want to improve the coverage. For example, in some indoor scenarios, when the user is blocked by some obstacles, right, from the base station, I mean that the signals received at the user side will be very weak, right? So in this case, if we have IRs deployed, right, we can establish a virtual line of sight link between the transmitter and receiver, right? We can let the signals transmitted here to bypass the obstacles and reach the receiver. And this is actually very important and useful for the future high frequency band, like millimeter wave and terahertz band, which are very sensitive to the blockage, right? So the second case is that we want to improve the network throughput, right? And traditionally, we like in the 5G, one of the key technologies is the ultra dense network, right? Ultra high dense network, right? Which means that we increase the number of the base stations. But this is at the cost of at high cost, the complexity, and also energy consumption, right? But in the future, we may deploy some passive IRs, as we can see the red one here, to improve it, to establish the local signal hotspot, and for example, at the cell edge or as some dense population areas to support our, for example, EMBB applications. The next application is to interference cancellation. As we can see here, a very simple two base station scenario. And typically when a user is located in the cell edge and its performance is very weak, is very, very low, right? Because it's in the cell edge, the direct link from its associated base station will suffer from high significant path loss, right? And also it suffers from the severe neighboring interference from the co-channel interference from the neighboring cells, right? So, but in this case, if we have IRs, right, we can deploy around the cell edge. On the one hand, we can improve the signal power by coherently align the signals from the direct link and also reflect link, right, to achieve the coherent combining at the receiver. On the other hand, if we know the channel state information of these two links, we can also suppress the interference from the neighboring base stations or cancel it and even cancel the interference, right? So this is a function of this, create a signal hotspot and also establish the interference free zone. The next application is that we want to protect our desired signals from the eavesdropper. And traditionally, if the eavesdropper is closer to the base station, it's very difficult to guarantee the physical layer security, right? Because the eavesdropper have a higher channel capacity. So in this case, if we have IRs, we can better solve this problem. For example, we can deploy the IRs either in the legitimate user, around the legitimate user or around the eavesdropper. As we can see here, we can tune the reflection coefficients of the IRs to more proactively reflect the confidential signals to the eavesdropper. Although it seems that the eavesdropper get more signals, right? But we can properly tune the reflection coefficients such that the signal confidential signals can be canceled at the eavesdropper. So this is a kind of to protect our confidential messages from the eavesdropper, improve our physical layer security. And the last application is the Swift system, right? And in the future, we may have a lot of information receivers as also as a lot of IoT devices, and they are wireless powered. So we can deploy an IaaS to improve the efficiency of the wireless power transfer and establish the so-called IaaS energy charging zone for the IoT devices here. And this is a vision of the IaaS for the future 6G, where the wireless radio environment is highly controllable and smart. And in the indoor case, IaaS can be attached to the ceilings, walls, and windows. And in the outdoor scenario, it can be attached to the building facade, lamppost, and even on the surface of the vehicles, as you can see here, to support different types of applications. So, so basically, the IaaS is a promising technology to make our infrastructure intelligent, and also helps achieve our future smart home and smart city. And here are some industry initiatives like Metawave, Greenwave, and Pivito. They have some demos and experiments results about the meta surface or IaaS equivalent technologies. And this is a more detailed summary of the industry initiatives. And if you have the interest, you can read our paper. And also, I was also invited to participate in the 6G white paper. And in the physical layer, the IaaS is also listed as one of the most important technologies. It means that our proposed technology has not gone unnoticed and actually has been well appreciated in our international research community. So here are some of the advantages of the IaaS over the traditional technologies, right? As we can see here, this is a 5G massive MIMO technology. The idea of the massive MIMO is very simple, right? It's just to try to blindly increase the number of the transmit antennas to achieve the three-dimensional beamforming, right? Although this is effective, but in practice, I mean, there's a lot of implementation issues like energy consumption, hardware cost, and signal processing complexity. And also, it is not scalable to the frequency, especially as the frequency goes up to the future terahertz band, right? But in the future, because we have the IaaS, we only need a very limited number of radio frequency chains and antennas at the base station side, right? So we don't need to worry about the scalability issue regarding to the frequency. And also, we can achieve the better performance by leveraging the large aperture of the IaaS, right? So because the IaaS is passive, so we have lower energy consumption and a scalable cost as compared to massive MIMO. And this is from the networking perspective. As we can see, traditionally, we have a lot of active components like macro base station, micro base station, relay or distributed antennas. Anyway, they're all based on the active nodes, active components, right? But in the future, we expect a new hybrid active and passive network, which means that we not only have the active components like a macro base station and micro base station, we also have the passive IaaS, right, to achieve a hybrid service for the users, right? So this kind of network is expected to have lower energy consumption, right, and a lower cost, but with much better performance in the future. So next, I will talk about several challenges. The first one is the beamforming, right? Let's consider a very simple scenario. If we have one access point, and also we deploy an IaaS to improve the user receive power here. And traditionally, when we can use the multiple antennas to serve this user, like MRT, a maximum ratio transmission, right, to beamforming towards this user. And also, we can also leverage the passive beamforming to serve this user, right? So especially when the direct link is blocked, right, we should design the beamforming at the base station towards the IaaS, and then leverage this link to serve this user. And also, on the other hand, when the AP IaaS link or the IaaS user link is blocked, and we better steer the beamforming of the base station towards directly to this user, right? So this is kind of a joint active beamforming at the base station, and also passive beamforming at the IaaS. And one fundamental result about beamforming design is that we found that when we increase the number of the passive elements at the IaaS, the user receive power will increase quadratically, This is known as the square power gain. As we know that for MIMO systems, we have a linear beamforming gain. But right now, by increasing the number of the passive reflecting elements, we have the square power gain. A more promising result is that we also prove that this is even holds by using practical low complexity and hardware, like 1-bit reflection, 1-bit phase shifters, right? We use the low-cost hardware. So this is some simulation result, and I consider a very simple scenario when the user moves far away from the base station between the IOS, right? And we we see the transmit power required at the access point for a given SNR target. And this is a simulation result, as we can see here. For the case without IOS, when the user moves far away from the base station in this direction, the transmit power increases monotonically, right? This is very intuitive because we have more path loss. For the IOS ADAS schemes, as we can see here, the transmit power, although the user is also very far from the base station, but the transmit power can still be very low. And also, as compared to the schemes without IOS, we have a significant power reduction at the base station side, right? So next, that is a fundamental performance limit. As I mentioned, this is a square power gain. We fix the transmit power at the base station, and we derive the expressions of the user SNR at the user side. So this is given by the squared form, quadratic form. Here, because this is mainly because from the AP to the IOS link, we have an aperture gain that is on the order of n. And from the IOS to the user link, we also have an acid beamforming gain. That is, so combine these two links, so we have the squared power gain. And later, we also showed that by using the bit IOS, for example, for each of the elements, we only have 2 values. And also, we derive the power loss by using the so-called discrete phase shifter. And we showed that the power loss has nothing to do with the number of the reflecting elements, which means that there's no accumulation error, even when we increase the number of the reflecting elements. So in practical systems, the implication is that we can enlarge, we can increase the size of the IOS to compensate the power loss caused by the discrete phase shifters. So this shows the greater potential of the IOS in practice. And also, as I mentioned, for IOS, because it's passive and also have a large number of reflecting elements, so the channel estimation is very difficult because it cannot transmit and also cannot receive, right? And also there's a large number of channel coefficients. And right now there are 2 main approaches. The first one is that we deploy some active sensors on the surface to to facilitate the channel estimation at the IOS. And this is and from this perspective, we can use the traditional channel estimation schemes. And for the other scheme, we do not change the architecture of the IOS, which means that we treat it as a totally passive one. We let the user send the pilots and estimate the channel at the base station. So this is known as a cascaded channel estimation. And there has been some very interesting schemes and also summary in our 2 papers. And also IOS as a new component, new devices, and how we deployed it in practical systems. Here I give a very simple example, right? As we know that for the traditional relay, it's better to deploy the relay in the middle of the transmitter and receiver, right? But for the IOS, right, as we can see, we can derive its user SNR expression, and we shoot the achievable rate versus the deployment, the distance, right? The distance from the access point. As we can see here, the optimal solution usually locates in the symmetrical locations around the access point and also the user. And also in the middle point, it achieves the lowest performance. It's worst. So this is very surprising actually as compared to the relay. This is the fundamental reason is that the IOS has double path loss channel model. It is quite different with the traditional relay. And also in practice, we have considered other factors like we want to achieve the beamforming gain or the spatial multiplexing gain for the multiple users. And also for multiple users distributed in the network, we consider the centralized IOS, right? Many different a large IaaS or distributed IaaS, right? Many different small IaaS in the network. So there has been some results in our recent papers. If you have an interest, you can read our paper online. And finally, we come to the conclusions. And I have introduced a new technology and to achieve the smart and reconfigurable propagation environments. It helps achieve the high spectrum energy efficiency as well as the low cost in the practical systems. And also there has been a paradigm shift of the IaaS from the traditional active component solely network to a new hybrid active and passive network. And also I introduced 3 major challenges from the communication and signal persistent perspectives: reflection, optimization, channel estimation, and also deployment. So there have been a lot of promising directions in the future work, like the reflection modeling, and also capacity and performance analysis, and also the combination of the IaaS with other technologies like massive MIMO, millimeter wave, and energy harvesting, and UAV. So here are some of the references in our group. So in the end of this year, we are going to have another tutorial. And this is one advertisement for our university. We're looking for the postdocs and PhD students. Okay, that's all. Thank you for listening.
Okay, thank you very much. Is there any questions? Okay, I just have one general questions, and
okay.
The topic of this workshop is focused on the combination of artificial intelligence with communications or communicating. How do you think AI could be applied in the IaaS? What's the contribution could AI bring into IaaS? Yeah.
Okay, thanks for the question. And this is actually a very interesting, probably a direction for the future work. As I mentioned for IaaS, right, we have 3 major challenges: the beamforming optimization, channel estimation, and IaaS deployment. In fact, actually, we can apply the machine learning techniques, a lot of these kind of techniques for all these challenges. I give a very simple example, right? So for the channel estimation, right? So in practical systems, in order to achieve this kind of a passive reflection, we can, at some stage, in the initial stage, we can use the IaaS, we can use machine learning techniques to learn the channel environment, right, from this architecture. And after we already have the training model, we can apply to the fully passive model to achieve the and without a channel estimation, which means that we can directly apply the beamforming based on our learning results, based on the AI techniques. Yeah, this is one promising direction. And also, I mean that in the future, we may also, for example, we have multiple IaaS. We can use some multi-agent learning techniques to achieve the coordination between many different IaaS. And also, for IaaS deployment here, I just explained some very theoretical, but in practice for IaaS deployment, we may use some learning techniques to predict where the optimal deployment location is. So this can be achieved by a lot of, for example, reinforcement learning techniques and also other techniques. Yeah.
Okay, thank you. Thank you very much.
So,
if
thanks.
there is no further questions, we will thank you again, Professor Wu, and we will move towards the next speaker.
Hello, may I ask a question?
Yeah, okay.
Yeah, because I put the question in QA. So nice talk. So I want to ask the question where should we deploy the IaaS for indoor users in the CG networks?
I'm sorry, I didn't get your question. You mean where to deploy?
Where to deploy the IaaS for indoor users in 6G networks? I mean, for example, if I want to use 6G at home, do I need to buy some intelligent reflecting surface and deploy them in my home or not? I'm just curious about it.
Okay, I know your question. You mean that in the future indoor scenario, how to deploy the IaaS, right?
Yes.
For example, in your unit, in your family, right? In your unit department, right? So
Yes.
I mean that it depends on how this technology can be leveraged by the operators. I mean that it can be a product, I mean, sold by the operators. In the future, maybe the China Mobile and China Union, they may sell this kind of service, right? Just like the routers or access points, right? And also, on the other hand, it can also, I mean, sold by the like a Huawei, this kind of company, right? Maybe they have some coordinations between them. I mean, yeah, this is how to achieve the coordination, I mean, between the operators and the industry, manufacturing industry. But in terms of how to deploy IaaS, here in the previous slides, I have some scenarios. For example, if, in some scenario, in some corners, your signals are very weak, right? And then you can deploy the IaaS, for example, in the ceilings, because usually from the ceiling, we can establish the line of sight channels. And also, as I mentioned in the last, in this here, if we have a lot of users, for example, in the future smart home, we have a lot of devices around in your table, right? And then we deploy IaaS to support this kind of service. But then we have to consider, we want to achieve the high beamforming gain or the spatial multiplexing gain. Because if each of the device require a dedicated information beam, I mean, different informations. But if you deploy the IaaS in the strong line of sight links, then the channel rank will be very low. So meaning that if you set up multiple data streams here, there will be very strong interference if the IaaS is deployed in strong line of sight. But so in this kind of case, we may to exploit the spatial multiplexing gain, which means that we can deploy the IaaS around some scatters to improve the channel rank of this combined channel. So this is some insights of the deployment, future deployment in the indoor scenarios. Yeah.
Okay, thank you for your answer.
Okay, thanks.
Okay, thank you very much. Due to the time limitation, we have to move to the next speaker. And if you have any additional questions, you can contact Professor Wu offline by email or something other ways. Thank you very much. And
okay,
thank you, Professor Wu. Okay, bye-bye. Okay, the next speaker is, sorry, let me sharing. It's Qingqing from China Mobile. And I also like to briefly introduce Dr. Qingqing. She is a senior researcher in China Mobile Research Institute. She is also a co-chair of O-RAN Working Group 2 and the chairman of the ITOT Focus Group on Machine Learning for Future Networks. She has been working on the key technology and the standardization of 5G radio access network. Now her research interests focus on various big data and AI for 5G and future RAN architecture, protocol, and algorithm design. His talk, the title of her talk is Towards Smart. Sorry, it's bringing AI into 5G radio access networks. Okay, thank you. And Dr. Sun, are you there?
Hi, Rongpeng, can you hear me?
Yeah, okay, yeah.
Okay, thank you for the introduction. Let me share my screen.
Okay, thank you.
Okay, thank you. First, I would like to thank for the organizers for inviting me. And it's my great honor to have these opportunities to share some work from CMCC China Mobile on bringing AI into radio access network. Okay, so first, as mentioned by the professor in the previous talk, the 5G is really coming, right, in our world. So from CMCC side, we had started 5G technology test 4 years ago, start from 2016. And in 2020, we already had commercialized a 5G network in China. So for now, we had already 250,000 5G base stations in China Mobile's network. So next page, I want to share more information about the 5G trends and also some paradigm shift for the 5G network architecture. So I think you must be quite familiar with the first and second trends in the 5G networks. So there is some rapid traffic growth in our network since we have a lot of short videos, for example, the TikTok, right, or surfing on that for every day. And then we have diversified services in 5G network. We have the ENBB, UILC, and also the MMTC. And with all these new features, the 5G network is becoming more complex, more complicated. We have more antennas and also more frequency bands. So here is an example. So compared to 4G network, we had 50 times operational complexity increase and more than 2,000 parameters for the typical 5G node. So it's quite difficult for the human to dynamically configure the network parameters to adapt to the changing environment to make it network really efficient for the users. Okay, so with all these difficulties, the 5G network had also done some great work on the evolution of network architecture. So first, the service-based architecture had been introduced into the network, and also the hardware-software coupling, the control plane, user plane coupling technology is also being introduced into the 5G network. Regarding the radio access network, the centralized unit and distributed unit architecture had been discussed and adopted as the standards for the 5G network. So with the centralized unit, we can do more coordination among different nodes to enable better user experiences. So with all these features, we do see that cloudification, service-driven orchestration automation becomes the main drivers for the 5G network and even beyond. So 5G network is becoming more flexible, efficient, scalable, and programmable network. With all this, we also envision some new features for the 5G era that is data-driven, right? In our network, we have a lot of data. So here we listed some real data types in our commercial network. So generally, we divide the data into 4 types. So the first one is about the business domain data. So we have the user subscription, the billing, or even the product marketing kind of information of the subscriber. And the second topic is more about the management data. And third topic is about operational data. We are more familiar with this part since that is quite related to the performance of the network. We also have the measurement data, the alarm in the network, and also some resource utilization information in the network. Last one, also which occupies the most data storage data is about the signaling data. So since our communication is based on the signaling between the Genome and the user, so we have different levels of protocols, right? We have the physical layer, mic layer, and in each layer we have a lot of signaling data generated every milliseconds. So there will be a lot of signaling data in the network. So with all these challenges that we see in the network and also amount of data we can collect it from the network, we just think the machine learning will play a quite important role in the 5G network and also helps to offer great opportunities for our network. So here I simply listed some opportunities we can see. So the first one is about the internal, that is more about the operator's internal digitalization, automation. The second is about the new it is able to provide new revenue streams, business models, and also diversified opportunities. With all this user level data, we may also provide more personalized network experience for the end users. And for the network, we can use all this kinds of data, the user historical behavior, and also some statistical analysis of the network data. We can improve network operation efficiency, reduce the human manual work, improve network energy efficiency, as well as the spectral efficiency of network. With all these opportunities, we also see some challenges here. So first one is about data. So what kind of data is useful, and where to collect, and how to efficiently utilize this data. There's a huge amount of data in the network, and all this data are stored in different nodes. Since in a radio access network, we do have a distributed network that is quite different from the data center. Okay, so the second question is about architecture. As we all know, the legacy network or the current 5G network is more designed for the communication rather for the machine learning. So we need to rethink and probably build new functionalities in the network to enable the machine learning enabled closed loop optimization. So the last but not least about algorithms. As we all know, optimization algorithm, for example, the convex optimization, have been well utilized in our network, and it really achieves good performance in our network. Why we need AI machine learning, and what kind of AI machine learning algorithms will be useful, and how to handle the robustness problem of all these AI machine learning algorithms. That's all the challenges we are facing. So next part, I would like to share more about the use cases we are considering on our commercial network. So first, as we all know, there are different types of use cases, and usually we started from the statistic or semi-statistic. We start from the operational management plan, that is for example, network planning, network deployment, network operation, and maintenance. A lot of this work had already commercialized in the network, since the data is quite easy to obtain, and also we had well-designed infrastructure to handle all this data based on the cloud platform. And moving forward, we do think when we consider bringing machine learning into the radio access network, we need to go from on the top to also to the embedded, to enable embedded intelligence in our network. That means we will leverage AI machine learning to also help to improve the performance for the control plan and also data plan. That means the protocol stack and even signaling procedure can be enhanced. The radio resource management algorithms can be optimized also based on all these data-driven and machine learning technologies. And even for the physical layer optimization, we all know that in the academic research, there are also a lot of insights happening there. So next page, as I mentioned, I would like to share more about the detail of the use cases from the time and resource categories. As we know, for the resources, we can divide the network resources into the size level, genome bin level, cell level, carrier level, and even the radio resource block level. And for the time granularity, we have different levels of control or management time granularity. So based on the resource and time granularity, we have divided all these use cases into 3 categories. The first one is more about non-real-time management plan. So as I mentioned, the data is more ready, and the platform, the infrastructure is also cloud-based. So it is quite easy to implement the AI machine learning or use AI machine learning to solve all these management optimization problems. So a lot of commercialized use cases are already being deployed in our network. For example, the network, the energy saving, I will share later. And moving down, we are now the whole industry and also paying more attention to the near real time a near real-time category of the use cases, which is mainly focused on the control and the user plane, which means the time granularity will start from the seconds, 100 milliseconds, and even to seconds. So the use cases here include the QoE optimization, load balancing, interface management in our network, which are more focused on the radio resource management part. And going further down, we will reach more about the use cases, but more which is more time stringent, which means that probably the control will happen more dynamically. For example, 1 millisecond or even 10 milliseconds. So here we have the multi-user scheduling, the link adaptation, and also even the AI-empowered physical layer design. So for this part, is more the current research status is more like the whole industry is doing more research on this. Is less mature than the management plan and the control user plan. Okay, so going further, as we all know, all these technologies need to serve our business goals. So here I would also like to share the use case from the business value driven point of view. So based on that, we simply reorganize these use cases into 3 categories. The first one is about service QoE assurance. It's more to provide customized network capabilities and service assurance for the diversified verticals. The second kind is more about the traditional communication technology enhancement to improve the network or efficiency. The third, the last one is more focused on the wireless capabilities power. The main goal is to provide value-added services. For example, the wireless positioning. We do think that will be quite important use case in 5G vertical scenarios and even for 5G beyond. So with all this, I like to highlight key technologies that we needed. First one is about data collection. Second is more about data ethics and AI machine learning functional framework. What kind of data functionality is needed in the network, and how to deploy all these functionalities into our real commercial network. That's the work we need further. We need further study. And the last one is about architecture and interfaces. What kind of architecture, for example, centralized distributed architecture, and how to do the machine learning model distribution and update. That's all the things we need to study. Okay, so moving forward, I would like to share the view on the architecture part. So here, we do think for 5G network beyond, it will evolve towards a deep city IT-DT convergence. That means the network will become more smarter, will be smarter and also more open. So here, the data analytics functionalities will be introduced in all the domains of network. For example, in the management plan, we will introduce the management and data analytics function. And for the core network, we have the network data analytics function already started in defined or standardized in 3GPP. And in the radio access, we do think we also need the RAN data analytics functionalities to enhance the radio as network optimization. Okay, so next part, I would like to share more progress on the standardization part. So here I list the overview of the research bodies and those parties and SDOs and open source activities in the industry on bringing AI into radio access network. So first, for the research part, we as we all know, we have the Future Forum, the Wireless World Research Forum in the Europe, and also for the IEEE, we have some emerging technology initiatives on the network intelligence and machine learning for communications. And for standardization, both ITU, 3GPP, ORAN, and ETI have started some work items and study items on the machine learning data analytics functionalities. And for the open source part, in the Linux Foundation, they established Linux AI project, which a lot of studies are happening there. So for example, we have ORAN, ONAP, Cumulus, ALIC, and PNDI. There are different projects that are working on how to implementing AI machine learning and how to integrate all these technologies with the network. Okay, so next page, I would like to share more details about the standardization open source activities for of the AI for wireless. So in 3GPP RAN 3 A2 SA5, there are a lot of study there on the data collection and utilization for the 5G network, and also the enablers for network automation for the core network, and the intent-driven management services, autonomous network levels are also studied in all these SDOs. And for ITUT, they established a focus group on the machine learning for 5G and future networks. So the main goal is to study the machine learning related interfaces, network architecture, and protocols, algorithm, data formats. So a lot of standard recommendation had already been released. So if you are interested, you can find more information on the website. And for the ORAN, the radio intelligent controller has been introduced into the radio access network. The goal is to enable the closed-loop automation, optimization of the RAN element resources, make it more intelligent, which means we'll introduce AI machine learning technologies, and more granular, that means the per UE or group UE level control will be considered more flexible. That means we will introduce intent or policy-driven optimization there. So for the open source part, as I mentioned before, the AI, the ORAN, ONAP, Cumulus, and PNDA, a lot of objects are studying on the AI data collection, network, embedded AI, and also network automation. Okay, so for the last part, I would like to share some use cases progress in our commercial network, and also there are some ongoing field tests in our lab and also in the network, 5G network. So the first one is about the machine learning for multi-rate and receiving. As well, we all know and receiving is quite an important feature for the 5G network. So here we had developed a multi-rate cooperation and receiving system for our 2G, 3G, and even 4G network. And now this system is evolving to also cover the 5G network. So all these kinds of network performance data is collected to our MCES platform. So in this platform, we utilized the AI machine learning to predict the traffic load and even analyzes the overlap coverage of different cells. So based on that, we will control to open or even stop the running base station to save the energy in our network. So for now, this system had already deployed in our network for more than 970 cells across 19 provinces in China. So that there are a lot of energies that are being saved based on this system. Okay, so the next use case is more focused on the radio resource utilization improvement. So in CMCC's China Mobile's 4G network, we had a lot of different bands in our network to provide more capacity for our users, but that also leads to some problems, how to do the load balance between different frequencies. It will be quite challenging problem here. For example, in our network, we have D1, D2, D3, FDD 1018. There are almost 8 or 9 different bands in our network. So optimizing the network parameters of the cell handover reselection among the capacity layer, the coverage layer, enhancing the coverage layer. and network traffic load will be quite challenging. So here we are leveraging the data collected from our network and machine learning technology. So first we can we will do some data cleaning and analyzing, and then we will do some clustering of the cells based on the user distribution and generating the solution using the training for different cluster cells. And finally, we will use a heuristic algorithm to find the optimized parameters in our network. So next page, we shared some real data collected from the network. Generally, they can divide into 4 categories. The first one is about site location data. The second type is more about the measurement data. For example, the reference RSRP information, the coverage information, and also some configuration data and performance data in the network. Okay, so next use case is more about anomaly detection. So as we all know, the anomaly happens in a network will cause a lot of human work to find out what's really happening, what's the problem in our network. But with the data analytics function, data analytics and all this KPI data and key quality indication data collected from network, we are able to do some automation for the anomaly detection and root cause analysis. Here, I won't spend much time here since the time is quite limited. Okay, so the next use case I would like to share is more about the network machine learning powered QE cross-layer optimization. As we all know, the video, and also even for 5G network, VR will be the killing applications in the 5G era. So how to ensure the user's quality of experience will be quite an important issue here. So to solve this, we think it's important to consider the cross-layer optimization between the radio access network and even the application server. So first, for the radio access network, we can try to classify what kind of traffic we are transmitting, and then based on this, we can do some QE prediction based on network conditions. For example, we can predict whether the video will store or not. If it is stored, we can dynamically enhance the scheduling algorithm to ensure the experience of the user. In another direction is that the network may also expose some RAN status, for example, the available bandwidth for the user towards the application server, so the application server can dynamically change the application coding rate so that the user will have better experience during all this during his services. Okay, so next page we shared a demo we are doing in our lab. So here we would like we utilize the data collected from the radio access network, for example, the UE channel status, the UE PDCP buffer status, the PDCP data rate, even the MAC rate, cell load, all this data. And with all this RAN data and the application level user stalling data, so we can make a prediction model to predict whether the video will store or not. So here we use a neural network LSTM network to train the network, and accuracy can achieve 19%. Okay, so with all these predictions, based on these predictions, we can increase the priority of the user scheduling. So the priority of the VIP video user can be upgraded and downgraded in real-time ways. Thus, the effectively guarantee the other users in network. So all the users in network can experience quite a good can have a good experience in the network. Okay, so the other work we are trying to work on also includes the AI-empowered beam optimization and also some link adaptation in the network. There are also some field trial test results. Okay. So last part I want to mention is about the open data set for the wireless network. So as we all know, for the NLP or even for the image processing, there are a lot of open data. So that really helped to improve the performance of the algorithm that help to accelerate the research progress in that area. And for the wireless network, we just think it will be really good if we can also have our open data set for the wireless network. So here is some preliminary consideration for the open data set in the wireless network. For example, we can divide the data into application layer data, user-related data, network layer data, physical layer data. And based on this data set, we can train some quite useful and machine learning model specifically for the wireless network. For example, the QE prediction, as I mentioned before, the mobility pattern prediction, the traffic prediction, network quality prediction, user distribution prediction. With all this well-trained machine learning model, it will definitely help to enhance the performance and network can be utilized for different network applications. Okay, so based on these sorts, we have started the first wireless big data competition this year in China. So we had 2 topics. So the competition is hosted by China Mobile and Huawei. So for these 2 topics, we had more than 100 teams join this competition, and good results have been achieved. And hope next year we can continue all this work. Okay, so last part is about lessons learned and also the challenges we are facing. So based on all this work and testing in our commercial network, we do think AI is just a tool. It's more suitable for the large dimensions, dynamic and complex problems. And data-driven, theoretical model, knowledge-driven intelligence algorithms are expected. And another important issue we need to consider is the balance between the performance gains and computation complexity. Since the resource in radio access number is quite limited, so how to balance the performance gains and computation complexity needs further study. And another thing to mention is about the wireless AI machine learning model generalization is extremely hard due to the dynamic network environments. So how to handle this problem? Probably transfer learning will be quite useful. That part also needs further study. And another thing to mention is about the edge intelligence with distributed reliable machine learning, federated learning, or collective intelligence, and how to enable all these advanced technologies in the radio access network, and what kind of use cases will benefit from these technologies is also open issue that we think needs further study. Last, as I mentioned before, the wireless open dataset is desperately needed to set up the algorithm benchmarks and boost the AI algorithm for the wireless. And hope we can all work together with all the partners in the industry to make some further progress on this. Okay, thank you. That's all my presentation.
Thank you very much. Is there any questions? Okay. Thank you, Dr. Sun. And I think with the AI combination of AI and the communication of computing into the cooperation both academia and industry. And as you mentioned, the wireless open data sets is an important part of the whole project, and we might be able to find some ways to work together. Okay, thank you very much. And we move to the next speaker. Okay, we move to the third speaker of this session. It is he is Professor Maziar Nekovee. And similar as before, I'd like to briefly introduce Professor Nekovee. Professor Nekovee is currently a professor of telecom and mobile technologies and Dean of Success, Zhejiang Gongshan Joint AI Institute and University of Success. He is also vice chair of the Network 2020 European Technology Platform, where he is chair of working group on future technologies. Professor Nekovee has been a significantly experienced researcher and was head of the Samsung research and development in 5G. His current research focuses on AI for radio access and core network design, terahertz communications for beyond 5G, 6G mobile communications, future internet architecture, and IP design for future verticals. Professor Nekovee is the author of over 100 papers, 15 patents, and 1 book. He has a PhD in physics and a first degree in triple E, both from the Netherlands. So today, the title of his talk is AI-based physical layer and protocol design towards beyond 5G, 6G radio access networks. So let's welcome Professor Nekovee. I will complete the sharing. Okay.
Thank you very much, Mr. Chairman. Can you hear me okay?
Yeah, I can.
Excellent. So I would like to thank the organizing committee for inviting me. It's a great pleasure and honor to present this truly excellent workshop. So I'm going to share my it seems I'm not able to share.
Okay.
You should have permission, so just click in the right arrow next to share screen.
Yeah, I cannot see my desktop.
Right,
Okay.
double click and then you will move from full screen.
Perhaps you can choose join Zoom, then you can share
Yeah.
similarly. Yeah, in a more familiar way. Yeah.
Yeah, we can see it now.
Right. Okay, thank you very much. So I hope you can hear me as well.
Yeah.
Yes.
It sounds great.
Yes.
Yeah.
So the title of my talk is AI-based physical layer protocol design towards beyond 5G, 6G radio access networks. And I'd like to acknowledge my collaborators, Dr. Wu and Lloyd Platt from University of Sussex, and Dr. Yue Wang from Samsung R&D UK. Just briefly, a little bit about our university. So we are in Brighton, UK, near the sea, not very far from London. I'm heading the Center for Advanced Communication, Mobile Technology and IoT there. And our focus is 5G and beyond 5G, as well as applications to what we call vertical sectors, including IoT, automotive, robotic, and more recently, health and artificial intelligence. And we work with a number of companies and industry which are hosted here, including Huawei, Samsung, and others. And we are involved in a number of European initiatives, such as 5G PPP, Network 2020, and also Telecom Infra project on Open RAN technologies. And we recently opened a joint education and research AI institute in beautiful Hangzhou with Zhejiang Gongshang University, which is going to train over 2,000 engineers in AI, robotics, and similar areas. So we're also very open and interested in new collaborations, in particular in China, in areas of joint interests, such as 6G, such as AI, and others. So just taking a step back to see about the sort of a mega trends that will be impacting the future of communications. So I think there are two really big trends, starting one with 5G and the other one really with the explosion of artificial intelligence. First of all, 5G is the first generation of mobile communication that is really moving into what we call new sectors, such as, so these are the verticals, such as telecom networks expanding into automotive, energy, health, robotics, and many, many other unknown territories. And this really is going to take off even bigger, more in 6G. This is a graph already a year old of the 5G already in China. But these new areas are really where we see very interesting challenges also. And the other trend is obviously the intelligization, meaning the artificial intelligence starting on the software and computing, also penetrating everywhere and anywhere. And this is a trend really accelerated from 2014 with deep neural networks and so on. There's a rising demand for AI in all kinds of systems. So the question we asked a few years ago, and I think there's now quite a large group of researchers working, is how would AI impact the next generation of mobile communication standards, meaning beyond 5G, 6G? When the 5G standardization started around 2015, in release 15, then AI was just starting to emerge big time. So it didn't have such a big impact in standardization. But with beyond 5G, we expect this to be more pronounced, and already we saw by excellent presentation from China Mobile that AI is really finding its applications in telecom domain already. And the other area is obviously the rise of these new verticals. We see networks for health, for robotics, for future applications. So networks are moving from familiar domains to new domains, new environments, new channels. And that has some implication for how we are going to design our networks in the future. Now, our interest has been in AI in a number of areas. So today we'll be focusing mainly on AI for the radio access networks. And these are some of the areas that I'll be focusing in particular in what we call model-free design of the physical layer. And I'll give you some example of research. But also we're working with some of our collaborators on other areas, such as the use of artificial intelligence for next generation NFV and SDNs on the core level, how we can combine AI and microservices in order to enable new NFV paradigms. And on the transport layer, so that is the front haul and back haul, we have been looking at things such as traffic pattern estimation and flexible functional split for front haul. Other areas that is of interest that we are not really working very much at the moment is redesign of TCP/IP for 5G and beyond 5G. And also give you an example of use of machine learning for reconfigurable metasurfaces. And this is for terahertz beamforming and beam tracking technologies. So this is just an example. I'm not going to go through the detail of this. So what we have done here is that we have demonstrated terahertz beamforming using metasurfaces, which is very similar to intelligent surfaces using liquid crystal. And we use basically AI and machine learning to, given a certain beam pattern, so far field beam pattern, how we can encode that in our reconfigurable, in this case, liquid crystal. And we use machine learning in order to solve this quite a difficult optimization problem. If you want more information about this work, we have just submitted a paper to IEEE Access, and we have a number of publications happy to share with you. But going back to the sort of my main focus is on the physical design. So basically the baseband of wireless communication systems, 3G, 4G, 5G, now moving towards 6G. So basically, and I've been very much involved at Samsung in design of the physical layer for millimeter wave. So when we design the physical layer, we obviously have a number of signal processing units. So we have source coding, channel coding, modulations at the transmitter. Then we have the same at the receiver. And that goes through a channel. And the aim of this is basically to enable the most efficient encoding under certain energy, latency, and other constraint in order to have the minimum, for example, bit error rate at the receiver. Now, this optimization problem is very well known and can be very tractable if we know the channel. So we have tractable models, mathematical models of the channel and the environment. And this is what happened with previous generation of mobile communications. For example, we spent quite a bit of time on developing the millimeter wave channel before we are able to design the physical layer for that. Now, that is fine, and these are obviously highly optimized. So you might ask, well, what is the performance gain if you're moving to using machine learning? Where is that coming from? Now, however, when we move to these new environments, and one of the previous speakers was talking about changing the property of channel using intelligent surfaces. So if you're moving to new environments, for example, in automotive or manufacturing, well, the environment is not known, then obviously that can be an issue. The other drawback is that if you're an interference channel, which is a channel that is not dynamic and not well known, then we also, as we will show, the conventional approach is suboptimal. And furthermore, by dividing the baseband, the physical layer into sub units, and then doing the optimization separately, we have an efficiency loss here. So a new approach has been emerged in the last few years, and there's this quite a pioneering work by Oshii and Hoydis, in order to basically, the philosophy here is that instead of having these signal processing units, we replaced the entire chain of transmitter and receiver and channel with a deep neural network and a special sort of deep neural network, which is called autoencoder. Now, what is the role of autoencoder? Autoencoder basically is a deep neural network that, given a presentation of say an image or something else, it will use correlations in order to reduce that to the most efficient presentation, and then that is then decoded on the other side. Now, in the context of wireless channel, basically what we use the encoder is to, we have given a number of symbols, we encode them in a most optimal way, given a penalty function, which is, for example, the bit error rate, in order to, at the receiver, then we have the optimal performance. Now, what are the advantages of this approach? Well, first of all, because it's an end-to-end solution, it will achieve a holistic optimization of the entire PHY processing blocks. It is data-driven, meaning that because we are using machine learning, and as I will show you, when we don't know actually the channel, so either we don't have a mathematical model for the channel, or channel is unknown, through learning, we're able to basically encode that information into our physical layer, rather than having to design our physical layer, then test it, and then change it. So we can update our physical layer quicker and can adapt to changing applications. So it's a data-driven end-to-end learning solution. It can help us reduce the design cycle of the physical layer of mobile communication systems. Now, we have been looking at a particular application here, and this is an interference channel. So when we look at the interference channels, well, basically, if you're looking, for example, as a scenario of dense deployment of 5G small cells, there could be a large amount of self-interference that will impact the character of the channel in terms of time dependence, in terms of nonlinearity, and so on. And therefore, this is really not the channel that our physical layer was designed for. And that will causes, that is one of the reasons that we get interference degradation. Obviously, there are other ways to deal with this, but one way to deal with that is that actually we adapt our physical layer to interference changes in our system. Here is a sort of a system overview of the system that we sort of prove the concept, at least through simulations. So what we have here is basically we have n pairs of transmitter and receivers transmitting and causing interference to each other. Now, instead of the conventional baseband, we have these autoencoders and decoders at both transmitter and receiver, so they can adaptively change. The channel itself is a dynamic channel because it is due to obviously the ambient noise, so the Gaussian noise plus the interference. And what we do is that we look at how this system then perform compared to conventional systems. And in addition to an autoconductor is a feed forward, so we introduce a feedback mechanism such that our receivers can learn the interference and then share that with the system in order to adapt basically the deep neural networks based on interference levels. So this is a paper just published in IEEE Access, so you can see the details there. Now, I'm not going to go through the further details of this, but the algorithm is basically, we have an AI model with specifications for our communication, and then we have also use pilot signals in order to make estimation of the interference that is then feed into our autoencoder in order to reconfigure our deep neural networks. So we estimate the interference, and based on that, we actually estimate the interference levels, we can adapt our results. Now, this first graph shows the performance of a single user. So the reason to do this is that we want to compare this in the single user with the conventional, say, PPSK or QPSK. Now, in this case, actually, we find that there are some subtle differences between the configuration for a conventional approach and us in terms of signal presentation. But basically, what we find is that our approach converges very well to the highly optimized BPSK and QPSK, except for some configuration where the representation of signals is actually quite different with what we have in conventional approaches. Now, the interesting results here that when you look at the multiple users, so we are here looking at the signal to noise ratio compared to BER. So as you can see that our approach to this deep neural networks has a superior performance compared to the conventional approach. So note that in none of these two, we are using any form of interference mitigation. So what we are doing is really we are adapting the constellation of our systems to the levels of interference. So it performs superior compared to conventional approach. We also have incorporated equalizer and everything else. This is very, very interesting. This is some details about how we can do this interference estimation. Basically is an iterative approach where we start with a guess for the interference level, and then we make estimates until we reach an optimal solution. Now, this is not a full reinforcement learning, so there's an adaptive procedure which can be further improved. But basically the message is that in the case of interference channel, we can achieve superior performance using autoencoders. Now, on the other hand, just a cautionary note that we find that when we don't have this adaptive interference, actually deep neural networks are more sort of, they are less robust to interference if we are not able to achieve that adaptive. This is another example where we don't have a centralized, so the first one was a coordinated approach where, for example, a mobile operator is coordinatively optimizing the interference of all its base stations, self-interference. This is an example of multiple systems operating the same frequency and they're not cooperating. So this is a sort of concurrent multi-user interference scenario. This is an example of a two-user case. So there are two users and each of them starts with an initial constellation and they adapt their constellation configuration to the level of interference by others. Now in the case of the two users, this actually can be formulated as a zero-sum two-player game. So it converges to a Nash equilibrium. So we can achieve convergence. When we go back to multiple users, we found that in this case of a distributed, non-coordinated learning, we are unable to achieve full convergence if we do simultaneous optimization, simultaneous learning. What we have to do is to do concurrent learning, where we start with a single pair that learns its constellation, then we add additional pairs, and this way we are able to achieve the Nash equilibrium. So this is another example. I'm not going to go to the detail of it, of how we can use, there's a concept called microservices for network function visualization, which we have basically a number of services. We turn them into small building blocks. Now, how we can actually optimize these microservices is a very difficult problem, and we propose to use machine learning and AI in order to achieve an automated microservice aggregation. The results are just published in this publication, so I invite you to have a look. So that brings me to the conclusion of my talk. So first of all, I believe that adaptive DL autoencoder is a very promising approach for design of next generation physical layer of mobile communication systems. It outperforms conventional PHY in scenarios where we have no a priori modeling of the environment, such as channel and interference, or it's not tractable, or it takes a long time. So we can look at things such as high interference 5G beyond 5G small cell networks, and also for vertical application. Some people are using it for molecular communication. For example, there's a kind of emerging area where the molecular channel is not known. Now we find that if we look at non-cooperative interference scenarios, we have a convergence and we are able to solve this with concurrent learning. So this is a very interesting example of sort of federated learning. Also, it may converge, and we're looking at potential solution. And ultimate goal would be to the next generation mobile standards, basically to reduce the time to standardization of new releases of physical layer. I think this is very also in tune with the emergence of things such as Open RAN, where allows operators or users to actually access the radio access part of the system and reconfigure that if required. And we're also looking at other applications such as front-haul protocol design and DL-based TCP adaptive protocols. And so we'd like to thank you very much for your attention, and we are very open to future collaborations. Thank you.
Okay, thank you very much,
Take
Professor
any
Nekovee.
questions,
Yeah.
if there are any.
Yeah, I think I have one quick question is that since URLC or ultra reliable low latency communications is an important part of the 5G. So for URLC services, it might be important for the accuracy or reliability. But as we all know, the machine learning might be something not so reliable. I'm not sure how do you think the application of machine learning in URLC for physical layer?
I think that's an excellent question. So obviously what we showed here was sort of online learning.
Yeah.
And that demonstrate how it can work in sort of interference scenarios. I think what we really are interested in is that a sort of a combination of online and offline learning, meaning that you will expose your, say, newly designed physical layer to unknown channels. You will learn from that, and then you optimize your design based on that. That means that ultimately what you have is say, a frozen deep neural network, and therefore this is not now subject to unreliable performance, rather than having an online learning system.
Okay, thank you. Okay, I think thank you very much, Professor Nekovee, and I think it comes to the end of this session. Session B, we will have a long break, and then we move into session C. Thank you very much. Noelia, you might enter the recording. Yeah.
Yes, I'll finish now recording. I'm also going to close the call because I need to do some check-ins to see if the recordings were okay. And I'll open it again in a few minutes. Is it okay?
Okay, that's okay. Thank you. Okay, bye-bye.
Thank you. Bye.
Thank you for inviting me. I will have another meeting, but I really enjoyed it.
Okay, thank you, Professor Nekovee. Yeah, thank you very much.
Bye-bye.
Yeah, bye-bye. That's one awesome. Bye-bye.